All right, welcome everyone. Today we're jumping headfirst into one of the biggest, most mind-bending questions in all of physics. We are going on a cosmic detective hunt to figure out if the very fabric of our reality is, a smooth, continuous canvas, or if it's actually made of tiny, indivisible pixels.
So this is the question, right? Is space-time continuous? You can see this pop up on a forum, and it's at the heart of our cosmic detective story. For the longest time, this was just pure speculation, something for philosophers to chew on, but lately a really surprising clue has popped up from a very, very unexpected place.
Okay, to really wrap our minds around what we're talking about, let's use an analogy. On the one hand, reality could be like a perfect, seamless painting. You could zoom in forever and ever, and you'd always find more detail, more smoothness. That's a continuous reality. But on the other hand, it could be more like a digital photo on your screen. From a distance, it looks totally smooth, right? But zoom in far enough, and you see it's made of individual pixels. That's a discrete reality.
So where does our investigation even begin? Well, our first piece of evidence, our first clue, comes from a tiny little particle that just isn't behaving the way it's supposed to.
So, say hello to the muon. You can think of it as the electron's bigger, heavier cousin. And just like a spinning top wobbles as it spins, a muon has this little internal magnet that causes it to wobble when you put it in a magnetic field. The speed of that wobble is called its magnetic moment. And this is where our story gets really, really interesting.
Now here's where things get wild. Our best rulebook for the universe, the standard model of particle physics, lets us calculate this wobble with just insane precision. But, and this is a huge but, when we actually go and measure it in our experiments, the number we get is slightly, but consistently different. It's like the official rulebook says one thing, but reality itself is doing something else.
And look, this isn't some tiny rounding error we can just ignore. As physicists Paul Davies and Philip T. put it, there is a persistent tension. In physics, they have this measure of confidence called sigma, and a 3.5 sigma result, well, that's a really strong signal that you're onto something real. It suggests something important is missing from our theories. It's a genuine crack in what we thought was a rock-solid understanding of the universe.
Okay, so a crack like that, it forces you to think outside the box, right? To look for a whole new explanation. And our prime suspect? It might just be the very nature, the very fabric of space-time itself.
And that leads us to this really radical idea. What if the reason our calculations are just a little bit off is because they all assume that space-time is perfectly smooth and continuous? What if, at some unbelievably tiny level, it's not? What if there's an ultimate pixel size to the universe, a point where you just can't divide space any further?
This theoretical minimum distance, it has a name, the Planck length. And I mean, look at that number. It's so small, it's almost meaningless to our brains. We're talking about a decimal point followed by 34 zeros and then a 1. This is the scale where our current laws of physics are just expected to completely fall apart.
Here's an analogy to try and make sense of this, and it's a wild one. Imagine you could take a single proton and blow it up to the size of the entire observable universe. On that colossal scale, the Planck length would be about the distance from Tokyo to Chicago. That is the theoretical pixel size of our reality, the ultimate boundary. Okay, so if space-time is made of these little pixels or atoms, then the next logical question is, what are they made of? This is where the investigation gets even deeper.
Well, one of the main contenders, one of the leading theories trying to figure this out is called loop quantum gravity, or LQG. It suggests that space-time isn't some smooth, passive backdrop for reality. Instead, it's an active, dynamic network woven from these unbelievably tiny, finite loops.
So what in the world does that actually mean? Well, LQG is basically saying that space has an atomic structure. These atoms of space are woven together into these complex webs called spin networks. And at this fundamental level, even things like area and volume aren't continuous. They come in discrete little packets, or quanta. It's a total reimagining of the stage on which reality plays out.
Now, to be clear, the physicists we're talking about didn't have to use the whole complicated LQG framework. They used something a bit more direct, a related model called doubly special relativity. You can think of it as a tweak to Einstein's famous equations. It keeps the speed of light as the ultimate speed limit, but it adds a second universal constant, a fundamental minimum length. It essentially bakes the idea of a pixel size right into the laws of physics.
And this
This is where it all comes together. This is the climax of our investigation. We've got the clue, that misbehaving muon, and we've got our suspect, the idea that spacetime is pixelated. Now let's connect the dots.
The logic they used is just so elegant. You can break it down into 4 simple steps. First, they just assume spacetime is pixelated. Second, they use that DSR model to recalculate the muon's wobble. And the result? The new number perfectly matches what we see in experiments. It completely explains the discrepancy. And the kicker is, their calculation actually spits out a prediction for how big those spacetime pixels should be.
And get this, the result they got is absolutely fascinating. The predicted pixel size is around 10 to the minus 22 meters. Now that is still ridiculously small, but it's a trillion times bigger than the traditional Planck length. What that could mean is that these weird quantum gravity effects might be much closer, much more accessible than we ever dared to believe.
So this new length scale, it corresponds to a certain energy level, about 30 tera-electron volts, or TeV. Now, you can think of TeV as the punching power of our particle colliders. Just for some context, the giant Large Hadron Collider, it currently runs at about 14 TeV. So we're actually getting close.
And that, right there, is probably the most exciting part of this entire story. The authors themselves say that this energy level might be within reach of the next generation of particle accelerators. This isn't just some beautiful idea on a blackboard. It's a theory we could actually test, maybe even in our lifetimes.
I mean, just stop and think about that for a second. This tiny little anomaly, this slight hiccup in the wobble of a subatomic particle, it could be the first concrete piece of evidence that our reality, our entire universe, is fundamentally pixelated. It's a clue that could change everything.
So you see how this incredible finding might solve one mystery, but in doing so, it just blows the doors open on an even deeper one. Because if reality really is made of these fundamental pixels, and you can't go any smaller, what lies in the gaps between them? Is it just nothing? Or is it something so fundamentally different our minds can't even begin to comprehend it? And that, well, that's the next great mystery.